In this video, I want to talk about an example of a vectorization of the computation of the gradient. I will be focusing on the example of linear regression, which you already saw in tutorial 1. I'll recap what you saw in tutorial 1 and then go a little bit further. The first thing I want to do is recast the linear regression model as a neural network. That's not very hard. So in linear regression, for a single training case, which has x, which is two-dimensional, so per one training case you have two x's, here's the output. The output is the bias plus the first weight times x1 plus the second weight times x2. This, of course, is very easily recast as a neural network with the output unit having an identity activation function. So the sum that goes into the output unit is going to be just the same as what goes out the output unit. That's your identity activation function. Now, when we do linear regression, it's often convenient to think about the bias as just another weight. In order to accomplish that, what you do is you say, we'll have another input, x0, which is always going to be 1. And then we have this additional weight, which is just going to be equal to the bias. That makes it possible to recast this computation, the bias plus the weighted sum of the x's, as just a weighted sum of the x's, which includes x0. We can rewrite this as the sum over I of wi, here you have the ones, but they're fixed, times xi. This can be written also as just w dot x, the dot product between the weight vector and the x, for a single training case again. Now, what about the derivative? The first thing that we need to do is we need to actually think about not one training case, but multiple training cases. Here we might think about the derivative with respect to the cost function for all the training cases, or you might imagine that you're using a mini batch, the way you would in project 2. Either way, what you would say is that the total cost is just going to be the sum over the costs for each individual training case. We said that our cost is quadratic, which means that it's just going to be the sum of the square differences between the output for case I and the actual expected y for case I as well. We can rewrite it as this kind of sum because this is what out I is. This is xji. There is a missing index I here. So, okay, if we want to take the derivative of this expression with respect to w1j1, so with respect to the jw, what do we get? Well, this 2 travels over here, and then we use the chain rule and say, well, we're taking the derivative with respect to the wj1j1, so the derivative of this function with respect to w1j1 is just going to be xj, because the rest of the x's don't influence anything because they multiply other w's, not this w1j1. So this is what we get. We get 2xji times the original function without the square, which is just equal to this. So here I went back and rewrote this expression as just w transpose times xi. As the dot product between the weight vector and the x, because at this point there is no point writing it out like that. The reason we wrote it out like that to begin with is because we were taking the derivative with respect to this guy, and then we would say, oh, you have the sum over the j of all of those, but when you're taking the derivative with respect to w1j1 for a particular j, you need to pick out the derivative with respect to it, which would be xj, this xj. Okay, so that is the expression. Now, if that's the expression, we can actually just code it up the way it is. Let's try to actually do that. So here I have the code from tutorial 1, and here is the computation of the gradient of f. So here I call it df. Now, what I'll do here in order to make things convenient is I'll just put a breakpoint here, and I'll run everything until I get to the breakpoint. Now, as you hopefully remember from tutorial, this is one of the ways to compute the gradient. So this here is going to be the gradient. Now, let's try to compute it without resorting to vectorization. So in a way, let's make things more straightforward by just using this kind of formula. So for the derivative with respect to wj is just going to be the sum over I of xji times w transpose xi minus yi. So okay, let's do that. So the first thing that I want to do is I want to say, okay, so what are the shapes of my x and my y and stuff like that. So here you'll notice that I've added a whole bunch of 1s to the x. Those are the things that we did in order to convert the bias into just another weight. So if we look at what the x looks like, well, that's not very illuminating. So the shape of the x is going to be like this. So let's look at the x, all the coordinates, but just, let's say, 5 of the cases. So here it is. And that's kind of what it looks like. So the x's are the columns of x, right? So x0 is always 1. And then in the first case, it's going to be 8.4 and minus 38, 17, stuff like that. Okay, so let's remember that the shape of x is like that. What about the y? The shape of y is like that because for each training case, we have just one output.